So yesterday we talked about the integration, right? And we've got a definition of the definite integral. We say that integration of the function from the interval a to the b is, by its definition, is the summation of the values of the function at some sample points multiplied to the delta x, and when we make this like a pieces, when we make the small pieces, right, and the number of the pieces will go to the infinity. So the limit of n goes to the infinity. So basically, if we would like to evaluate the area under the curve in the interval between a and b, we have to divide this interval between a and b into the n small subintervals, right? Do you remember this? So that was the width, which is delta x, which is b minus a, divided to the n, right? So the delta x, which will be the width of each subinterval, b minus a divided to the n. Then we'll split this to the n small rectangles, right? And by finding the sum of the areas of all the rectangles, we will roughly evaluate the area under the curve, right, in this interval between a and b. Then, yesterday, we also calculate the error, right? We can calculate the error if you know exactly the area. And by subtracting this from the approximate area, which we did using the rectangles, we can know what is the error, right, which we make. It appears this error goes to the 0 if we increase the number of the partitions, okay? So if n goes to the infinity, then the error between the actual result and the approximate result goes to the 0, okay? So this is the definition of the integration. So obviously, we're not going to evaluate the integrals like this. At least analytically, we're not going to do this, okay? So in practice, this is very useful to know this formula because in practice, it is difficult to integrate many functions, okay? So usually, people implement the numerical integration. And this is like, so for example, previously, we've learned about derivatives, right? And we define this using the limits. But not so examples. So in practice, we don't usually use the limits in order to find the derivatives, okay? Most of the time, as engineers, okay? But like as engineers, we use the numerical integration a lot in practice, okay? So because most of the time, it is really difficult to integrate the functions. So it is better to use the numerical integration, okay? So that is why, in order to understand how it works, how this formula works, you need to implement this in a computer and submit this as a software project, okay? There will be a software project on the numerical integration. You'll be given a function, and your program should ask me a, b, the intervals, right, and n, okay? How many pieces it should divide. And it should tell me the answer, what is the numerical result, and what is the error which you make. Okay? So this is what your program should tell me. So today we will continue learning the integrals. We will continue with the fundamental theorem of calculus. So fundamental theorems of calculus. So there are two fundamental theorems of calculus. The first one tells us, so if my function g of x is given as, or let me write it as s of t, okay? So s of t is given as the integration of the v of x dx until the t, then it appears the derivative of the s with respect to the t will be equal simply to the v at this point, okay? Do you understand this t? It's like I'm finding the derivative of this s function at some point t. It appears that at this point t, its derivative is equal to the simply v, okay? You don't need to integrate this and take the derivative. You can just take the v as the answer. So the conceptual idea is like this. So do you remember we talked about the distance and the time, right? So we say that, hey, if the function of the distance has this kind of form, then if I take the derivative at some point like t0, what does it mean? The slope of the tangent line is the derivative, right? The slope of the tangent line means the velocity, right? If I take the derivative from the s at some point t0, it tells me the instant velocity. Velocity exactly at this instant of time, right? Then also we've learned about another problem, right? If we're given the function of the velocity, let's say the velocity is constant, 60 kilometers per hour for 1 hour and for t hours. So how much distance you will pass in t hours, within t hours from 0 until the t, if your velocity is constant? Is 120, right? Which seems to be the area under this curve, right? You see, so if you find the area, the width is 2, the height is 60. If you multiply this, it will be 120 kilometers, right? So basically, if I integrate the curve of the velocity, it will tell me the distance passes through in this interval, right? For example, if I decide to integrate this from 1 to the 5, then it will tell me how much distance I passed, right? In between the 1 hours and 5 hours. Okay, so let's assume that the function changes. Now, let us build the function. Okay, so the function will be like this. So if you choose some point t, t is now is the variable. Okay, it tells me the distance which you passed until this point t. How I need to construct this? So t now is the variable. Do you understand what does it mean, the variable? Right? For example, t is equal to the t is the constant, right? You fix this, that's it. So t is we call the variable if you can change it, if you can play with this, right? If it takes a lot of different values as well, okay? So now, depending on t, it should tell me the distance, okay? So for example, if I plug the t to be equal to the t, so write a function in a computer, okay? It asks me the t, okay? And if I type, for example, t, it tells me the distance I passed until the t hours, okay, until t is equal to the t. Then it asks me again, so what it tell me the t. If I write 5, then it should tell me the distance which I passed until 5 hours, okay? So how it looks like geometrically, what I need to find? I need to find the area from 0 until this t, right? Do you understand this? So the area until this t will be equal to the distance which I passed until the point t, until t hours, right? So how I can write this algebraically, using calculus, I can write this as the integration of the velocity curve, right? Or let me write this now with respect to another variable from 0 until the t, right? Or dx here, dx. Do you understand this? So if I would like to find the distance which I traveled until the point t, I need to integrate this curve from 0 until the t, okay? It will tell me the distance which I passed from 0 hours to the t hours, right? This will be s of t. Do you understand this? Yes? So now I'm asking you, hey, if I choose one point t here, you know the velocity, the function of the velocity. I'm asking you, what is the velocity at the point t? What is the velocity at the point t? It's this point, right? So what is the velocity at this point? It's simply this point, right? You don't need to take the integration first and then take the derivative, right? You can just evaluate the velocity function. You know this velocity function, okay? This is what the fundamental theorem of calculus 1 tells you, okay? If you've got the function of some variable, where the variable is on the borders of the integration, then when you take the derivative of this function, this will be simply equal to this function. Okay? So let's do an example. For example, let's say s of t is equal to the integration of the sine of x dx, okay? From 0 until the t. So first, what I will do, I will integrate this first and take the derivative, okay? And secondly, I will use the fundamental theorem of calculus in order to answer the question. Using the fundamental theorem of calculus 1, what does it tell me? So it tells me that s prime of t is equal simply to the sine of t. Right? So it tells me that if the variable is on the border of the integration, then if I take the derivative of the s, it will be simply equal to the sign. This is what the fundamental theorem of calculus 1 tells me, right? Now, we can check it by integrating this function first and take the derivative with respect to the t, right? Whether this is equal to the sign or not. So if you integrate this, what you will get? What is the antiderivative of the sign? So far, we don't know how to integrate this, but let's assume that for a moment, for 1 minute, we know this, okay? So this will be minus cosine of x. We need to evaluate this at the t and at the 0, right? So this will be 1 minus cosine of t, right? Because if you substitute, it will be minus cosine of t. If you put the 0, it will be 1. With the minus, it becomes plus, right? Now, s of t, it appears, is equal to 1 minus cosine of t. So what is the s prime of t? No. Like this. So what is the s prime of t? Is sine of t, right? So which is the same as what does the fundamental theorem of calculus 2 tells me, right? Do you understand this? If you take the integration and find the derivative, you will get the same answer as you would just take the function, which is under the integration. Okay, do you understand what does it mean? Okay. Then the second fundamental theorem of calculus tells us that fundamental theorem of calculus 2. It tells me that if I would like to evaluate the definite integral from a to the b, f of x dx, then this will be equal to the big F at the point B minus big F at the point A, where this big F is called the antiderivative of the small f, right? What does it mean? It means that the derivative of the f, big F, is equal to the small f. Okay? So sometimes we call this theorem as Newton-Leibniz formula. Newton-Leibniz formula. Theorem or formula. So you've seen this before. So let's do an example. So let's integrate, evaluate to integrate from 0 to the 1, 4 plus 3x squared dx, right? So in order to evaluate this using the fundamental theorem of calculus 2, first of all, we need to figure out its antiderivative, right? So the antiderivative of this function will be equal to the 4x, right, plus x cubed, right? Why? Because if I take the derivative from the 4x plus x cubed, I will have 4 plus 3x squared, right? So this is the antiderivative of the function, which is under the integration. So now we need to evaluate this at the 2 points, at the point 1 and at the point 0, and we need to subtract them, right? So put the 1, basically, it will be 4 multiplied to the 1 plus 1 in the cube, minus, put the 0, 4 multiplied to the 0 plus 0 in the power of 3. So this will be equal to the 4 plus 1, which is equal to the 5. Okay? Good. So this is the fundamental theorem of calculus 2.